Now we are going to consider some other heat conduction problems, some other heat conduction problems. Basically, we are going to consider only two other problems. The first one, boundary conditions non-zero. And the second one, where the boundary conditions. The second problem we are going to consider where the ends are insulated. Both of those conditions affect the boundary condition. The initial condition is again going to be the initial heat distribution function, a function of x. So our main equation is the same. Main equation is the same. U sub t equals alpha squared U sub x x. So for the first problem, boundary conditions, the boundary conditions at the end where x equals 0, it is going to be kept again constant temperature, but not 0, some temperature T1. And at the other end, the temperature is going to be T2. So ends are kept at constant but non-zero temperatures T1 and T2. Well, not both. When I say non-zero, not both are 0. T1 or T2 may be 0, but not both. This is going to be the previous problem we consider where ends are kept at constant 0 is a special case of this condition. The ends are again kept at constant temperature, but now they may be non-zero. So when they are 0, when they are 0, it's going to be a special case. All right. Now, if you remember, at the end of part 1, I said in the case where ends are kept at constant temperature 0, we obtain this infinite series for the solution. And because of the negative exponent in the exponential part, the limit as t goes to infinity is 0. So that limit we call the steady state heat distribution. So limit as t goes to infinity of u x t, this is going to be a function of x because we are taking the limit as t goes to infinity. So it's only going to be a function of x. It is called steady state temperature distribution. When both ends are kept at constant 0, we expect the steady state temperature to be constant 0. But here, the ends are again kept constant, but not at 0. So for we write the general temperature function as the sum, the solution, as a sum of the steady state solution plus another, not xy, xt, plus another part, or if you want, you can consider this other part w to be the temperature distribution minus the steady state distribution. So the limit as t goes to infinity of this part is going to be 0. For the steady part, steady state temperature, Vx, now what do we expect it to be? Since it's going to be the steady state, it's not, once the system, the heat distribution reaches the steady state, it's not going to change again. It's going to stay at it's going to stay at the same state, this Vx. Eventually, the heat distribution is going to be this function. So since, okay, so as you move along the rod, so this is going to be some function of x. Of course, this temperature in this steady state, it's going to change from point to point because, first of all, at the ends, this temperature T1 and T2 doesn't have to be the same. But that change as x changes, that change itself is not going to change. So the second derivative of the steady state temperature distribution, we expect it to be 0. So the second derivative of this steady state temperature is going to be 0. And at the end where x equals 0, it is going to be T1. And at the end where x is equal to L, it is going to be T2. So from this information, we can obtain, first of all, second derivative 0 means it's a linear function, C1x plus C2. Since it's at x equals 0, the value is T1. This is C1x plus T1. And when x equals L, it is T2, so C1L plus T1. So the constant C1 is T2 minus T1 divided by L. So this function Vx, is going to be the difference T2 minus T1 divided by the length of the rod L times x plus the temperature at the end, x equals 0, which is T1. So the steady state temperature distribution is going to be this linear function. So it's going to change linearly from one end, x equals 0, to the other end, x equals L. So it has to be this function. So now we need to find the solution u. We need to find this function w. But now w is going to be w is just u of xt minus vx. So w is going to satisfy the main equation. So the partial derivative with respect to t of w is going to be partial derivative of u with respect to t, because v doesn't depend on t. It only depends on x. So its derivative with respect to t is 0. And the derivative with respect to x is going to be u sub x minus v prime. So the second derivative is going to be u sub x minus v double prime, but v double prime is 0. So w, second derivative with respect to x of w is the same as second derivative of u with respect to w. So w also satisfies wt equals alpha squared wxx. U satisfies this equation. So, but since the relevant derivatives of w are the same as the derivatives of u, w also satisfies this equation. Now, what about the boundary conditions? What is w0t, for example? It is u of 0t minus v of 0. U of 0t is t1, but v of 0 is also t1. So w at the end, at the boundary x equals 0 is 0. At the other boundary, it's also going to be 0 because it's u of lt minus v of l. Both of them are t2. Okay, so wxt is a solution of a boundary value problem wt equals alpha squared wxx, w0t equals wlt equals 0. But that's the problem we considered in the previous lecture. So we know that it is given, the solution is given as this infinite series Cn e to the minus alpha squared n squared pi squared t over L squared sine of n pi x over L. Okay. Now, what are the constants, Cn's? Remember, they are given by 2 over L, integral from 0 to L, the function W0, Wx0. Yes. So the initial, okay, maybe first I need to write it separately. So what is the initial condition? Initial condition is the heat distribution at time 0. So that's V of x0, sorry, U of x0 minus Vx, right? U of x0, we take the initial heat distribution to be the function f. So for the function w, the initial condition is the initial condition of u minus this steady state solution, steady state distribution v. So the constant Cn's are given by 2 over L times the integral from 0 to L. Instead of f, we have f minus v of x times sine n pi x over L v x. And once you find your constants, here is v, here is the constants, and then your solution is going to be vx plus the sum n from 1 to infinity, Cn, where Cn's are given by this formula, e to the minus alpha squared n squared pi squared t over L squared sine n pi x over L. So the only difference is for using the temperatures T1 and T2, you find this function V, and using that function and the initial heat distribution F, look at these integrals to find the constants and write your solution in this form. the example here is going to be the same as the example I did in the previous video. You need to evaluate these integrals. Okay, let's do an example. So, example. Let's say the number alpha squared is 0.8. The length of your rod is 20. Boundary conditions, at the end x equals 0 is 0, but at the end x equals 20, it is 60. And the initial heat distribution is 25. Under these conditions, let's find U of xt. Okay, so the temperature T1 is 0, at the end x equals 0. So temperature T2 is 60. So the steady state heat distribution, Vx, is, by the way, you can consider this form of the solution. Where is my form? This form, I write my solution as Vx plus W. You can consider this W as the solution of the homogeneous problem. For W, the boundary conditions are 0. So you can consider this W as the homogeneous problem. It's the part which involves with the constants. And the Vx you can consider as a particular solution. So the solutions, we again follow the same, the theory follows the same lines. Homogeneous solution plus a particular solution. The only difference here is using the physical situation, we obtain this particular solution, and using the particular solution, we write the homogeneous solution. But the form of the solution is again the same, homogeneous solution plus a particular solution. So the particular solution, T2 minus T1 over Lx plus T1. So T1 is 0, T2 is 60, L is 20, 60 over 20 is x, so Vx is 3x. Okay, Vx is 3x. And then I need to look at the difference, the initial condition F minus Vx. Initial heat distribution is 25 minus the steady state is 3x. So the constant Cn, 2 over L. L is 20, integral from 0 to 20, 25 minus 3x times sine n pi x over L. L is 20, dx. Okay. Again, we need to do this integral. Maybe we should have done it in the more general form. Okay. So first of all, 2 over 20 is 1 over 10. For 25 times sine, I have 25. Antiderivative of sine is minus cosine. I need to take 20 over n pi cosine n pi x over 20 from 0 to 20. Minus, I have the constant 3. Remember, for this integral, we call x as u and the remaining as dv. Then du is dx, and v is minus 20 over n pi cosine of n pi x over 20. So minus 3 times u times v minus 20 over n pi x cosine n pi x over 20, x from 0 to 20, minus plus 20 over n pi, integral from 0 to 20, cosine of n pi x over 20. Okay, 1 over 10. 25 times 2500. So minus 500 over n pi. Now, if we substitute x equals 20, we have cosine of n pi. Minus, if we substitute x equals 0, cosine of 0 is 1. Okay, that's for this. Okay, minus 3 times minus 20 over n pi. So plus 60 over n pi. If we substitute x equals 20, 20 cosine n pi. Minus, when you substitute x equals 0, is going to be 0. Then minus 3 times 20 over n pi minus 60 over n pi. Ni derivative of cosine is sine, but we need to divide by the coefficient of x, sine n pi x over 20 from 0 to 20. Okay, so 1 over 10. Minus 500 over n pi cosine of n pi plus 500 over n pi plus 1200 over n pi cosine of n pi minus 0 minus 1200 over n squared pi squared. When I substitute x equals 20, sine of n pi minus, when I substitute 0, sine of 0 is 0, but sine of n pi is also 0. So it is equal to 1 over 10, 1200 minus 500, 700 over n pi cosine of n pi plus 500 over n pi, right? And the 10 we can simplify. So Cn is 1 over n pi, 70, 50, 10 over n pi, 7 cosine n pi plus 5, right? Okay, what is cosine of n pi? It is, what is cosine of n pi? If n is even, like 0, 2 pi, 4 pi, 6 pi, it is 1. And if n is odd, 3 pi, 5 pi, so this is minus 1 to the n. If n is odd, it's minus 1. So it's 10 over n pi minus 1 to the n times 7 plus 5. So if n is odd, it is minus 2, this number. And if n is even, it is 12. But we can leave it like this. So this is our Cn. Then our solution is Vx, which is 3x, plus n from 1 to infinity, the constant Cn, 10 over n pi, minus 1 to the n, 7 plus 5, e to the minus alpha squared, remember 0.8, n squared, pi squared, t over L squared. L is 20, so it's 400, sine of n pi x over 20. Okay. Now, for the second case, insulated ends, it means no heat flow through the ends. That changes the boundary conditions because now the ends are not kept at constant temperature. There's no heat flowing through the ends. So we take the ends together with the whole rod. They are not kept constant, okay? But there is no flow. That means now heat flow is proportional to heat flow through a cross section. This is a physical phenomenon, so that's also given information. Through a cross section is proportional with what? Let me see. The cross section is proportional to the rate of change of temperature in the x direction, so U sub x. So no flow through the ends, it means we have the boundary condition. No flow means U sub x should be 0 at the ends. So U sub x at the end x equals 0, and U sub x at the end x equals L are 0. So instead of U, partial derivative of U with respect to x at the ends are constant 0. So this situation, insulated ends, changes the boundary condition. That means we need to start the whole process all over again. Since the boundary conditions are changed, they are not boundary, we don't have the value of U at the boundaries. We have the value of the derivative with respect to x at the boundaries. So we start from the beginning. Again, we use separation of variables. We look for solutions of the form a function of x times a function of t only. The main equation doesn't change. U sub t is alpha squared U sub x x. So U sub t is going to be the function x times t prime equals alpha prime. U sub x x is going to be second derivative of x times t. So that's the first part is going to be the same, alpha squared. So x over x double prime is going to be, what am I doing? T prime over alpha squared t is going to be equal to x double prime over x. So since one side is a function of t only and the other side is function of x only, this is going to be constant, and we call the constant minus lambda. So we get the pair of equations, x double prime plus lambda x is equal to 0, and t prime plus alpha squared lambda t is equal to 0. So these are the pair of equations. Now, boundary conditions. U sub x 0 t. This is going to be x prime 0 t times the function, I'm sorry, x only depends on x. X prime at 0 times the function t at t. And since this is equal to 0, we want non-trivial solutions, so we don't want the function capital T to be 0. So we have x prime 0 equals 0. And similarly, from the other boundary condition, x prime L t of t equal to 0. So from here, we get x prime L equal to 0. So we have the boundary value problem, x double prime plus lambda x equal to 0, x prime 0, and x prime L equal to 0. So this is our boundary value problem. So we are looking for non-trivial solutions. Our equation is constant coefficient, linear, ordinary differential equation. So we write a characteristic equation, and it depends whether this number lambda is negative, positive, or 0. So case 1, lambda negative, we let k to be square root of minus lambda. Minus lambda is positive. And the roots of the characteristic equation, plus and minus k. So the solution is C1 times e to the kt plus C2 e to the minus kt. Now, for the boundary conditions, we need the derivative. So derivative is k C1 e to the kt minus k C2 e to the minus kt. So if we use the conditions, x prime 0, x prime 0 is k C1 minus k C2. This is 0 means C1 minus C2 is 0 because the number k is not 0. Lambda is strictly negative. And x prime L, k C1 e to the k L minus k C2 e to the minus k L equal to 0. So you can divide by k, and from the first equation, C2 is the same as C1. So we can rewrite this as C1 times e to the kl minus e to the minus kl equal to 0. But this number is not 0, so we have C1 equal to 0, and that means C2 is 0. So in case lambda less than 0, for lambda less than 0, there is no non-trivial solution. The only solution we get is the 0 solution. So we take the second case, lambda equal to 0. In that case, the equation is simple, x double prime equal to 0. So x is C1 x plus C2. So derivative is C1, and because of the boundary conditions, that constant C1 must be 0, since x prime 0 equals x prime L is 0. But we don't get any condition for C2. In the derivative, C2 disappears. So we have a non-trivial solution. If you take C2 equals 1, non-trivial solution for lambda equals 0. So Remember in our previous problem where the ends are kept at constant temperature, we do not get a non-trivial solution for lambda equals 0, only for lambda greater than 0. So here there's a difference. We get a non-trivial solution for lambda equals 0. Constant solution, but it is still, we may have a constant, non-zero constant solution. So what is the corresponding solution for t? T, what was the equation? T prime plus alpha squared lambda t equals 0. For lambda equals 0, the equation becomes t prime equal to 0. So t equals c constant is a solution. So the corresponding solution u of xt is going to be c constant. So for any constant, we get a solution. Okay. Again, let me remind you, in the previous case, we had this infinite series, but the series starts from n equals 1. We did not have a constant part. In this case, we do get a constant, okay? And for case 3, lambda positive, so we take k to be square root of lambda, or lambda equals k squared. And the solutions, in this case, when you take lambda to the other side, it becomes negative. So the roots of the characteristic equation are going to be complex. So the solution is going to be C1 cosine kx plus C2 sine of kx. So if you take the derivative, minus k C1 sine of kx plus k C2 cosine of kx. So the boundary condition x prime 0, if you put x equals 0, sine 0 is 0, cosine 0 is 1, so we get k times C2. If you take it equal to 0, we get C2 equals 0. So you see the difference now. C2 is 0, so we don't have the sine function in the solution. We are just going to have the cosine function. So instead of a Fourier sine series, we are going to obtain a Fourier cosine series. Okay, so other condition, x prime L. Since we already obtained C2 equals 0, so I'm just going to take C1 cosine of KL equal to 0. Since C2 is already 0, to obtain a non-trivial solution, C1 should be non-zero. So we need cosine of KL to be 0. Because if C1 is 0, then we get trivial solution. For non-trivial solution, we consider C1 non-zero, meaning cosine of KL is 0. So when is cosine 0? Cosine is 0 cosine is 0 when wait, no, I'm sorry, in x prime. C2 is 0 in x prime. What am I doing? In x prime, it is minus k C1 sine of KL equal to 0. So I get sine of KL equal to 0. Not x, I'm using x prime. My boundary condition is about x prime. So sine of KL 0 means KL must be a multiple of pi. So n starts from 1, 2, 3, and so on. Okay, so the number k is n pi over L, and lambda is k squared. It is n squared pi squared over L squared. All right, so the solution x we get is, we take C1 to be 1, just get one solution, cosine of k, which is n pi x over L, for lambda equals n squared pi squared over L squared. So now we need corresponding solution for t. So t prime plus alpha squared lambda t equal to 0. But the solution here we already know. The solution is t equals e to the minus alpha squared lambda t. And lambda is n squared pi squared t over L squared. So for each n, 1, 2, so on, we obtain the solution u sub n, which is e to the minus alpha squared n squared pi squared t over L squared times cosine of n pi x over L. And for lambda equals 0, we have u0, which is constant. But remember, for the Fourier cosine series, the constant term we take to be C0 over 2, because in the integral we get a 2, cancel with the 2, we take C0 equal to 2. So we get the solution C0 over 2 plus the sum n from 1 to infinity, Cn e to the minus alpha squared n squared pi squared t over L squared cosine of n pi x over L. And the constants are now 2 over L times the integral from 0 to L, the function f of x times cosine of n pi x over L, including the constant C0. In order for this integral formula to work for all Ci's, instead of just C0, we take C0 over 2. So again, all we have to do is substitute the values for alpha squared, L squared, and evaluate the coefficient Cn using these integrals. So I need to do an example of this case to finish our lecture. So we consider a rod with length equals 40, constant alpha squared equals 1, initial temperature U sub Ux0 equals sine of pi x over 40, x between 0 and 40. What else? Ends are insulated. So we have the cosine series case. Ends are insulated. What other information do we need? Okay, so the question is, find the temperature and the steady state temperature what is the steady state temperature? The limit as t goes to infinity of u x t. Okay, so we know that the solution has this form. And the constants Cn's are given this way. So our function uxt is of the form C0 over 2 plus the sum n from 1 to infinity Cn e to the minus alpha squared is 1, n squared pi squared t over L is 40, so 1600 cosine n pi x over 40. So the coefficients, 2 over L, integral from 0 to L, the function as sine of pi x over 40 times cosine n pi x over 40. Okay, so I'm going to do, all right, so how do we take this integral in general? To take this integral, we use this trig identity as sine A times cosine B is 1/2 sine of A plus B plus sine of A minus B. But when we take A minus B, here sine pi x over 40, cosine n pi x over 40, when we take the difference, when n equals 1, the difference is going to be 0. So I'm going to do the case for n equals 1 and n equals 0 separately, and then for n greater than or equal to 2, we are going to use this formula. So for C0, I have 2 over L, integral from 0 to L. Since n is 0, I have cosine of 0, which is 1. So all I have is sine of pi x over 40. And antiderivative of sine is minus cosine, minus 2 over, no, what is L? L is 40. So this is 1 over 20 minus 1 over 20, 40 over pi cosine pi x over 40 from 0 to 40. So when x is 40, cosine of pi is minus 1. Let's see, I have minus 2 over pi. When x is 40, cosine pi is minus 1, minus when x is 0, cosine 0 is 1. So I have 4 over pi. C0 is 4 over pi. For n equals 1, C1 is 2 over 1 over 20, integral from 0 to 40, sine pi x over 40, cosine of pi x over 40. So the angles of sine and cosine are same. Sine A, cosine A, that's 1/2 of sine 2A. So 1/2, I have 1 over 40 sine of 2 of pi x over 40, so pi x over 20. Remember, sine 2A is 2 sine A cosine A. This is what I use. So again, antiderivative minus, where's pi? Yeah, minus 1 over 40, 20 over pi cosine of pi x over 20 from 0 to 40. So minus 1 over 2 pi. If I take x equals 40, 40 over 20 is 2, cosine 2 pi is 1. Minus, if I put x equals 0, cosine 0 is again 1. So this is 0. C1 is 0. All right, so for n greater than or equal to 2, Cn 1 over 20, integral from 0 to 40, sine pi x over 40, cosine n pi x over 40. And I'm going to use the trig identity. I'm going to write this as 1/2 sine of a plus b. So 1 plus n pi x over 40 plus sine of a minus b, 1 minus n pi x over 40. Okay, so 1/2 meaning 1 over 40. Ni derivative here minus 40 over 1 plus n pi cosine of 1 plus n pi x over 40. And minus 40 over 1 minus n pi cosine 1 minus n pi x over 40 from 0 to 40. Okay, I can take 40 over pi out, so minus 40 over pi out, so minus 1 over pi, 1 over 1 plus n. If I put x equals 40, I get cosine of 1 plus n pi, right? Plus, minus, when I put x equals 0, cosine of 0 is 1. Plus 1 over 1 minus n. If I put x over x equals 40, I have, let's write it this way, cosine of 1 minus n pi minus, when I put x equals 0, I get 1. So minus 1 over pi. Yes, let's keep it this way. Okay, let's keep it this way. Now, cosine of n plus 1 pi depends whether this number is even or odd, meaning depending on n. If n is even, then okay, first of all, cosine of 1 minus n is the same as cosine of n minus 1, because cosine of minus x is the same as cosine x. Cosine is an even function. So when n is even, remember n is greater than or equal to 2. When n is even, then n plus 1 and n minus 1 are odd. So cosine of 1 plus n pi and cosine of n minus 1 pi are both minus 1, right? When it's odd multiples of pi, cosine is minus 1. Then Cn is minus 1, both of them are minus 1, so this is minus 2. Cn is minus 1 over pi, minus 2 over 1 plus n, minus 2 over 1 minus n, which is, let's take minus 2 out, 2 over pi 1 minus n plus 1 plus n over 1 plus n, 1 minus n, 4 over pi 1 minus n squared. If n is even. If n is even. So if n is even, Cn is given like this. If n is odd, then n plus 1 and n minus 1 are even. So cosine of 1 plus n pi and cosine of n minus 1 pi are both 1. But when they are 1, you have 1 minus 1, you get 0. Cn is 0. So Cn is 0 if n is odd, 4 over pi 1 minus n squared if n is if n is even. That's also in accordance with the first two constants we find. We find C0 to be what was C0? 4 over pi. So here, if you take n equals 0, it's an even number, 0 is even, n equals 0, 4 over pi. So the formula works for n equals 0. And for C1, we found it to be 0, and 1 is odd, it is 0. So this is for all n greater than or equal to 0. This formula works. So the solution then is n even means, okay, let's see, n even, so I can write n as 2k. Then C of 2k is 4 over pi 1 minus 4k squared. Okay, so I can write my function. Remember C0 over 2. C0 is 4 over pi over 2, so 2 over pi plus the sum k from 1 to infinity, because I have only C sub 2k, 4 over pi 1 minus 4k squared, e to the minus n squared is 4k squared, pi squared t over L squared, 1600, cosine n, which is 2k pi x over 40. So I can simplify this. E to the minus k squared pi squared t over 400, right? If I simplify by 4, cosine of k pi x over 20. And the second part of the problem, steady state solution, limit as t goes to infinity of u x t. In this infinite sum, the negative exponentials are all going to, the limit is going to be 0 because k starts from 1. For k equals 0, we write separately 2 over pi. So the limit is going to be the constant 2 over pi. So eventually, the temperature on the rod is going to be constant at 2 over pi. Constant temperature. It makes sense, right? Ends are insulated, no heat escapes. So the heat eventually is going to distribute evenly. So we expect it to be constant, and that constant is 2 over pi. Okay, so this is the end, the very last thing we do. Of course, mathematics never ends. As I said, there are more cases, more equations, partial differential equations to consider. In this course, we only, the main purpose of considering this problem is to show you how the method of separation of variables work, how to get the boundary value problem from the method of separation of variables, then how to find solutions of that boundary value problem, and how to put them together as a Fourier series to obtain the solution of your heat conduction problem and finding your constants using the Fourier theorem. So I don't know how much you enjoyed it. I know it's been hard for the last couple of months, but the end is near. So I just hope that all of you are doing fine, and the semester will end to your benefit. I hope to see you all later in better circumstances. So that's all for this semester.